Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so we continue our discussion with respect to heat. Okay, and last time we were looking at the kinetic theory of gases. Now we are going to transition a little bit to this subject called thermodynamics. Okay, now thermodynamics, always it's good to start a little bit with kinetic theory of gases and then look at its interaction with thermodynamics. Okay? Now, thermodynamics is a field unto itself, and it is, particularly through the 19th and 20th century, what was learnt from the study of thermodynamics in terms of energy and in terms of entropy and in terms of heat and the transfer of heat was dually applied in both physics and in chemistry. Now, even today, the applications are more in both of these fields. Okay, in physics, thermodynamics and fluid mechanics and all these, these interactions with heat and movement, right? And the movement of heat and the movement of power, have been so central to the industrial revolution. This is so because of the because the industrial revolution has revolved around the manipulation of energy. Notably energy derived from fossil fuels. The two main fossil fuels that provided energy for a long time were coal. Coal is the king coal, they used to call it. King coal, and later oil. And with the emergence of coal and the internal combustion engine, thermodynamics got onto a got a fantastic reception. So they first had the steam engine, then they had so then they used it in locomotion. Then they had the steam based thermal power when electricity was invented and they needed to make energy, right, for electricity. It always started with the burning of coal. And so later, of course, electricity also got another source, natural gas, which is used today in the United States. Most power is generated from natural gas. Not so in countries like India, China, and Germany, and I guess also maybe Japan. But mainly India, China, and Germany, where the vast majority of its power is generated through the burning of coal. US uses natural gas more. But that said, the phenomena involved are pretty much the same or similar. And so because of its role in transport, because of its role in the transfer of power from fossil fuel to other forms of movement and to electricity, thermodynamics became a great science. Okay, so that's an introduction for you for thermodynamics. But it's also very sophisticated, beautiful science. And so for those of you who are going to be in both electrical engineering or mechanical engineering or metallurgy or chemical engineering, these are the main sciences. All of you know chemistry is the central science. So it's heavily used in chemistry. So So thermodynamics is worth learning. The human body, right, has its own sophisticated mechanism in the manufacture or the conversion of energy, you know, and there also that transfer of energy from food to all the things that we do. We think, we eat, we do physical work, we run, right? Same with all the animals. You see all these fantastic animals in the TV, right? See these big whales, you see these tigers and all that. They also have a bio related thermodynamics. Well, I wouldn't, it's not exactly thermodynamics, very chemical in its nature. But then, these, the movement of these energy sources, the movement of this energy through the body, through what is called the Krebs cycle, movement. And same with plants. Plants get their energy, of course, from even more sophisticated. They manufacture it like your solar panel, right? Every plant is in its own way. Solar panel. How do you have energy, right? Today, they use the sun, you know. So it is an amazing world we live in. And, as we like to say in JnanaMarga, or as so beautifully put in the song, I don't know whether it is Kalyanji, Anandji, or whoever else, ये कौन चित्रकार है, ये कौन चित्रकार है, it doesn't just apply to the biological world, also applies to how all the physics works and how the chemistry works, and how the sun enables this luscious planet with all this great life, who is, as the Upanishads say, Mataraswan, who orders the waters and establishes life. Anyway, let's continue with that introduction to thermodynamics. So the first ideas that we deal with in thermodynamics, okay, the first ideas we deal with is the definition of various parts. It's a systems of science. It is probably the first systems of science that was devised. So we will look a lot into this just now. Okay, so let me bring up. So the system is whatever we study. It is a very system science, and therefore they always teach thermodynamics in the first or second semester in college, with a view to kind of giving you the feel for system science. It may be as simple as a free body, okay, so or as complex as an entire power plant. We may want to study a quantity of matter contained within a closed, rigid walled tank, or we may want to consider something such as a pipeline through which natural gas flows. So that's a system, so you're looking at the whole system. Now, the most common thing is to look at what are called closed systems, but you can also have open system. Now, a closed system consists of a fixed amount of mass, and no mass can cross boundaries. That is, whatever mass you're studying, that there is no exchange of it with some other, Now, so that non-movement of the mass that's being studied from inside to the outside, outside to the inside. Other things may move, like energy, but not the mass itself. The mass stays. Volume of a closed system does not have to be fixed. Okay? Even energy is not allowed to cross the boundary. Okay? Then, if that happens, it is more than a closed system. It is an isolated system. Okay, so the energy doesn't change. Also, that is, all the energy is held in. Okay, but most often you rarely deal with isolated systems, except when you are actually doing your own physical test, in which case you try to isolate everything and then you study everything. Now, an open system is called a control volume. In a control volume, things come in and things go. For instance, in a control volume, right, is probably, selected region in space, usually encloses a device that involves mass flow, such as a compressor, turbine, or nozzle. Okay, so there's something coming in, some operation done on it, and then it is let out. Right now, I'll give you two examples. Okay, your air conditioner. Okay, inside your air conditioner, they have this freon gas. Okay, now that freon gas becomes liquid, then gas, then it comes back to liquid, so it keeps flowing in a closed circle. So that is not a control volume. That is a closed system. Okay. But on the other hand, if you look at your car, right, with its tremendous IC engine, right, the car is always putting exhaust out. You put gasoline in the tank, that's coming in, right? There is air from the surrounding atmosphere that comes in, burns the fuel, and then the exhaust, it goes out of the exhaust, right? So that is it is usually enclosed a device that involves mass flows as an air compressor, turbine, or nozzle. The other case is like your conventional steam engine, right? The steam engine also involves uh, coal that is used to heat water. The water itself, right, very often, eventually becomes vapor and is let to go out, right? But in some cases, it's kind of circulated. When that happens, like in the AC, it's different. But when you pour water and then it becomes steam, and then that drives the engine, and then it's let go, then it's a lot different. Then we say that it is a control volume. Okay, so all these things, and then the system does work, right? Now, in the case of the thermal power reactor, right? Thermal power reactor also, there is coal, which then drives steam, and then the steam heats up. The coal's energy in coal's the CO2 that is generated, other gas, silicon dioxide, because coal also contains other materials, sulfur, which also burns, silicon dioxide, some nitrogen, etc., nitric oxide, many things that come from the burning of coal. After all, coal is almost like a tree that was kept underground. Think of coal in that form, right? And trees, as you know, contain nitrogen, phosphorus. Trees are they have a great requirement for phosphorus, which is found in the fertilizers, right? And so, but it's those trees, of course, got phosphorus from the from natural sources, right? And then, of course, carbon and the nitrogen, carbon, Krebs cycle, right? Now, when coal is burnt, it produces CO2, and today CO2 is a greenhouse, considered a greenhouse gas, right? Now, and that is let out, right? So now, but then there is the heat is captured and transferred to a form of energy, which is first, which is typically electrical energy, the form of the engine that is made to run. The system boundary should be carefully defined before proceeding with any thermodynamic analysis. In general, choice of a system boundary is governed by two considerations. Okay, what is known about a possible system, particularly at its boundaries, and the objective of the analysis. Note the second one. Okay, the objective of the analysis that defines the system boundary. Okay, so sometimes you are just interested in the transfer of energy. The transfer of energy is central in several of the processes that I outlined. The air conditioner sucks the heat in a room and reduces its temperature. Okay, and then it passes it on to some other place, the outside. You know, I've never known anyone who wants to go sit behind the AC in the hot days, right? Now, similarly, in the case of the steam engine, there is the inbuilt latent energy, chemical energy, through thousands of years of where coal was made underground, right? It was a plant first, it went underground, became coal, or it was an animal, and then it was buried underneath, and then it became coal under enormous pressure. Now that coal is burnt, right? So it converts what is latent chemical energy into heat energy, and that heat energy is then used to build to then drive to steam, convert to steam, and then steam drives the engine, right? So now there are two kinds of views in thermodynamics. There is the macroscopic view, which deals with the gross behavior of the system itself, and this is what you will mostly deal with in this class. It is called classical thermodynamics. No model of the structure of matter at the molecular level is directly used. They look at gross overall behavior. So I burn this much coal, and so it's an aggregate of all the heat. I burn this much coal at this rate. It leads to this much energy being transferred to the gas. That drives the engine of some sort, whether it's to run the car or whether it is for the thermal power, right? And then that gets converted to energy, to either movement, kinetic energy, or it gets converted to electrical energy. So that is the macro understanding, classical thermodynamics, and and then we go on. Now, of course, it's also used in metallurgy, right? So chemists are used at both the classical level. Now, there is another kind of thermodynamics known as statistical thermodynamics. Statistical thermodynamics is to study the average behavior of the particles making up a system of interest and relates this information to the macro. There is statistical, which then explains the macro. And this is also very, very important. For instance, there are what are these called, in fluid dynamics, Navier-Stokes equation. Then there is the flow equations in chemistry. Then there are other equations that deal with this understanding of the microscopic and the macroscopic. And more so in statistical thermodynamics is also used, to better understand at a very micro level what happens also. So for a wide range of engineering, classical thermodynamics not only provides a more direct analysis approach for analysis and design, also requires far fewer mathematical complications. So it gives a very good understanding without excessive over study. Classical thermodynamics. That's the important advantage of classical thermodynamics. This class is not about the second one, statistical thermodynamics. That's if you at a later date you do more advanced courses in either as a physicist or as an engineer, you will then learn little more about statistical thermodynamics. Now, property is a macro characteristic of a system: the mass, the volume, the energy, the pressure, and the temperature. Okay? Heat can be thought of as a form of transferable energy. Okay. Now, the state refers to the condition of the system as described in the values of properties. Okay. Now, what are the various values of properties? Right. When any of the properties of systems change, it undergoes what is called a process. So you have property A, property B, it goes from state 1 to state 2, right? So what are all the things that can change? The volume can change, the pressure can change, the temperature can change. You've seen all this in the context of PV equals nRT, the gas, ideal gas equation, right? PV equals nRT. If I keep N constant, how do P and V change? Boyle's law, right? So those are also in some ways the rudimentary uses at a rudimentary level. They are thermodynamics. Okay. A process is a transformation from one state to another. Now we say that if a process is isobaric, what is isobaric? Isobaric means that the pressure does not change. Okay, then you can have isothermal or isochoric. Okay, the system is given in initial state, right? Goes through a number of changes, and then it or process, and then it comes back to that initial state. Then it has undergone a cycle. Sometimes you don't have a cycle. Okay, most notably in when you deal with something which is passing through a controlled volume, doesn't go through a cycle. For instance, the gasoline that is put into your car, right? You go to a petrol bunk, you put it as a gasoline there, right? And eventually it goes out of your exhaust as a mixture of gases, including CO2, right? Mainly CO2, but also other gases that kind of leave the exhaust of your vehicle, never to return, right? So that is a non-cyclical process. While I gave you the example of the fridge or the air conditioner, the freon gas, it goes in a cycle. It goes through a cycle. So the system that you study, the mass that is being studied, it goes through a cycle of properties and it stays in place. Property is called extensive if it you have to add all the parts inside it, and you have to sum it up to give you the total, where there is a accumulation. Speed is not an extensive property, right? If but then mass is an extensive property, right? Speed, or for that matter, pressure or density or even temperature, right? These are all intensive properties. That is, they are independent of the full extent of the system. Okay? So it is not so with mass or volume, right? You keep adding more, then you get more mass or volume. So that is called an extensive property. Now, intensive is like temperature, right? Now, some examples of specific properties are specific volume, right? Now, you can also have extensive properties for which you have a associated per something, per unit volume, right? So density is like that. Right? Density is a mass per unit volume, right? So now it's an extensive property per unit something called a specific property. Specific heat, right? Etc. Per unit mass. So per unit something, it's called a specific property. Okay. Now, in a thermodynamic system, there is this thing called an equilibrium, and it is most important in chemical, because chemical equilibrium is a very central idea. There is what is called Le Chatelier's principle, etc., which come into play in the context of a chemical equilibrium. My suggestion is you please learn this very, very carefully when you go back to your chemistry class, because there it's a far more important subject in physical chemistry, and it gets applied repeatedly in physical, and you must understand that part very, very well for your chemistry as well. So that's why I keep telling you a little bit about that. Now, mechanical equilibrium is related to pressure, okay? And a system is in mechanical, there's no change in pressure at any point of the system. Thermal equilibrium is there if the temperature is same to the entire system, and the system is there is no temperature differential, which is the driving force behind heat flow. Okay, so now things reach thermal equilibrium means T1 becomes almost the same as T2. There's no therefore transfer of heat after that. Mechanical equilibrium means there's no change in pressure. Chemical equilibrium, the chemical composition does not change with time. That is, there is no chemical reactions happening. Okay, or there is a net balance between the two sides as part of the chemical reaction. So now they are in balance, chemical balance. Okay, they are what are called balance equations. So quasi-equilibrium process. Um, uh, so can I'm giving a physics class. So can I call you right back? I'll call you in about half hour. Half hour. Okay, thank you. So a quasi-equilibrium process is one in which the deviation from thermodynamic equilibrium is infinitesimal, and all the states the system passes through during a quasi-equilibrium process may be considered equilibrium states. So now there is what we call a reversible process. The moment the weight is removed from the piston, mechanical equilibrium does not exist. As a result, the piston moves upward until equilibrium exists. So quasi-equilibrium process can be viewed as a sufficiently slow process that allows the system to adjust itself internally so that properties in one part of the system do not change any faster than those in others. For non-quasi-equilibrium processes, we are not able to characterize the entire system by a single state, as we cannot speak of a process path for a system as a whole. So now a non-quasi-equilibrium process is denoted by a dashed line between the initial and final states instead of a solid line. Okay, so now, so that is the difference, between a quasi-equilibrium process, right? Versus a non-quasi-equilibrium process. So, things are happening only at a certain pace, and they're happening gradually, right? We say it's a quasi-equilibrium process. Non-quasi-equilibrium process, cannot speak of the system, process parts of the system as a whole. Things are little more dynamic. So now here, the system, right, is going from an initial V to a final V, and the pressure is correspondingly going up. So this is the P versus V diagram of a compression process. So this is a quasi-equilibrium process. Why is it a quasi-equilibrium process? Because it's happened somewhat slowly, and it allows the system to adjust itself internally. The properties do not change any faster than those of the other parts. Now, work is the energy transfer associated with a force acting over a distance. The work done by a system is evaluated, as you all know from your mechanics, F dot dx. F is the force applied over a displacement. The dot product of the force and displacement leads to work being done. Okay? Now, in a system, also work is done. There is, let's say you are compressing a a given volume, right? You are doing work, and that work manifests itself in greater pressure, right? And it manifests itself in other forms, sometimes in the form of heat. Work is done, and the system, or its temperature increases, etc. Right? So now work done by this is a very important idea. Work done by the system. So when there is work done by the system and it transfers energy to the outside, we say it's positive. When someone does work on a system, we say it is negative. Work done on the system is negative. Okay, so now isobaric, as I said, pressure is constant. So if you have P dV, right? Integral P dV is work, right? Then you have PV, right? So P times V2 minus V1, right? Now, if you have instead, V is constant, then it's an isochoric process. Then you have zero, right? Because P dV will be zero, right? So now, if it is a constant isothermal process, why does it become like this P1 V1 ln V2 by V1? It is because when you integrate, this is in the, if you say PV equals nRT, right? So, because T is constant, right? You can write P as nRT divided by V. And because T is constant, you can remove nR and T outside, and therefore you have dV by V. Therefore, when you integrate dV by V, so in isothermal process, you end up with this PV ln V2 minus V1. For isochoric, because the volume doesn't change, there is no work done. Similarly, if you have PV to the power of n equals constant, we call it a polytropic process. Therefore, you then have these equations. My advice to you is to take a look at how this works, by doing PV to the power of n equals constant and then doing this integration, polytropic process, right? This is a n equals 1, you end up with this one. This is not a polytropic process. N cannot be 1 here. Okay. So if n is 1, notice that 1 minus 1 is 0, right? So this integral is wrong. This integral only works for isothermal. Okay. So now heat is defined as the form of energy. Heat is a very surprising thing, okay, that is transferred across the boundary of a system at a given temperature to another system at a lower temperature, virtue of the temperature difference between the two systems. Again, just as we saw here we saw work done by the system is positive, work done on the system is negative. It's the other way around. When in the case of heat, when work is done on the system, it is positive, unlike here, while when there's heat transfer to the system, it is positive. When there is heat transfer to the outside, it is negative. So the property temperature distinguishes thermodynamics from the other sciences. Heat as a measure of hotness or coldness, right? So temperature distinguishes thermodynamics from other sciences. Temperature as a measure of hotness or coldness. Okay, so these are all the ideas involved, right? When we studied the kinetic theory of gases, we made certain assumptions, right? All collisions between molecules or between a molecule of gas and a wall are perfectly elastic. All gases are made of molecules moving randomly in all directions. The size of a molecule is much smaller than the average separation between molecules. And then we had this Maxwell speed distribution function, P of V versus the speed, right? And from that, we ended up with, the probability of finding a molecule with speed V at temperature T is given by this expression. So it's a probabilistic equation, right? And therefore, they said that, you'll have different molecules, and at VRMS is the most probable speed is different from the VRMS, is different from the mean speed. And one is 3RT by M. Remember, VRMS is root of 3RT by M for based on kinetic theory of gases, V average, etc. You can do the integration and find out. Okay, so integral, if you do, you will end up with the average, and you can also get the most highest you get by, which is the highest of a equation like this. You take the derivative and set it to 0, right? Why do you take the derivative? What happens when you take the derivative and set it to 0? You get a maxima, right? So if you have a curve, how do you find the maxima? Take the derivative, set it to 0, right? So, and when you take the derivative of this, set it to 0, you will end up with the most probable speed. Okay, so this Maxwell speed distribution curve gives you most probable speed, also gives you the mean speed, and then finally VRMS. Okay, so the average speed in a Maxwell distribution is therefore determined. See, he is doing the integration for the average, right? He's doing the integration for the average, and then from that you can so you integrate, you get the average, you differentiate, you get the maximum, and then you can also do the root mean square, right? That also is a probability integration. That also can be obtained from a probability integration. So you take v minus v bar the whole square and you integrate 0 to infinity, then you get the other one, VRMS. But for that, you can first calculate the V average. Okay. So now, so that's how root mean squares are calculated. The complete derivation can be taken from the video. We've already seen this. You have a box, and then you have all these particles moving, and then we look at it as a collisions, right? We look at the collisions, the distribution of different velocities. We say that the collisions are perfectly elastic, and the molecules exert no forces. They behave in a certain way, and then we did, and that's how we got 1/3 rho c square, right? Or 1/3 m by v c square. You remember, and then this 3 kt by m, right? So those were the key ideas that we had, and let me bring up the next set of slides here in terms of thermodynamics. But the core thermodynamics essentially deals with the first set of ideas, that is, we have a system, control volume, then we deal with macro behavior. So those ideas are very, very you start there. Those are the basic concepts. Then we continue. Now we already saw KTG, right? So I don't want to do KTG too many times. You already know how KTG behaves, and then we had TV equals nRT, and then we found that a more realistic view is to have this V minus NV and T plus A by V square is nRT, right? Then we had these isotherms, right? Now, in the case of thermodynamics, macroscopic approach to understanding thermal properties of matter, coarse-grained description, you have P, V, and T. You have thermodynamic variables, right? So the system is okay. Now we're going to discuss the first law of thermodynamics, which is actually another way of stating in a closed system, right? Of of stating a conservation of energy law. The first law of thermodynamics is long considered another way of dealing with the energy conservation in the context of these mechanical systems. Okay, so law of conservation of energy, you all know, right? Energy cannot be created nor destroyed, right? So that is restated in the following way in the context of thermodynamics. If the quantity of heat supplied to a system is capable of doing work, then the quantity of heat absorbed by the system is equal to the sum of the increase in the internal energy and the external work done. So for that, we have to remind you as to what we said with respect to the convention. If you remember, in the first set of slides, we had this convention that when there is work done by the system, it is positive, and when there is energy absorbed as heat transfer to the system, it is also positive, right? So now transfer to the system leading to work being done by the system, right? So so therein we saw we state the first law of thermodynamics, right? Heat transfer. to the system, work done by the system. So the quantity of heat supplied to a system, that's positive, right, equals the quantity of heat absorbed, which leads to internal energy increase of the system, is external work. Okay, so let's explain that a little bit, right? So when coal is used to, uh, boil water in a steam engine, right? There is heat that is absorbed by the system. Okay, that heat increases the energy of the water, which absorbs, which absorbs what is called latent heat of boiling, right? Latent heat of boiling, right, generates this gas, right? And then the gas itself, also increases in temperature, right? So then heats up and then that does work. What is the final work? The final work is the movement of the train, right? So that is the work done. Then there is this heated gas. Not all the coal that you burn, not all the heat that you transfer to the gas becomes motion of the train. Some of it is absorbed into the internal energy of the steam, and then it goes into the atmosphere as part of that. Okay. Similarly, all the internal, when you burn the coal itself, some of it will, not all the energy that is inherent in the coal will be released. You will be able to transfer it to the closed system of the plant. Okay, so that is a very, very critical idea. So the first law of thermodynamics deals with this idea that however, there is full conservation of energy. Okay, so now we already discussed extensive and intensive variables. Intensive is independent of the amount, right? Extensive is more the merrier, right? So now the system is divided into two equal halves in equilibrium. Pressure and temperature are unaffected. So walls and the interactions. Adiabatic wall system is insulated, only mechanical interactions positive. Diathermic walls, heat exchange, thermal exchange is possible. Porous walls for particle exchange. No ideal wall, there are approximations. So these are all the notion of equilibrium and quasi-static process. PV equals nRT, right? So there is thermal equilibrium, mechanical and thermal equilibrium. So these are all the ideas that I have time for today, and we already discussed all these ideas. So so what I am going to now do is I'm going to start here in the next class with the first law of thermodynamics, which deals with the conservation of energy, and we will look at the various cases. First, when we supply heat. Second, when the system supplies heat. First, when we do work, right, etc. So what happens with that closed system? How does it work? So think of it as how we repeatedly look at the steam in a steam engine and how it does work with moving our train, and then we do heat transfer to it by burning coal. The engine driver, you are the engine driver, you're putting coal, you're burning the water, you're heating the water, right? So mechanical is the mechanical work that is done leads to the train moving, right? So we will discuss this dq equals delta u plus delta w, okay? And so that is a very central equation. Then we will discuss PV equals nRT. So the internal U is PdV, so the work is PdV, right? And the internal U leads to its energy increasing, internal energy increasing. And we look at that equation, how the internal energy, what part goes to the internal energy, what part goes to the work that is done by the system, the percentages. Those are essentially the ideas behind this. But we will come back to this set of slides when we will take things forward from there. Okay, so these are the simple ideas with respect to thermodynamics. We look at closed systems. We have a lot of definitions in terms of the ideas here, and then using these, we will then build the you will move towards understanding these other terms like entropy, and finally, we will also understand the system behavior. Okay. With that, I'm going to close for today, and we will re-engage next week when we continue with thermodynamics again. Okay. So with that, I'm going to end, and we will continue next week. All right. Thank you very much. Have a great week, and I'll see you next Saturday morning IST. And for students who are looking at class 12, we are going to start semiconductors and electronic devices. We'll discuss transistors. We'll first discuss how semiconductors behave, transistor as a amplifier, and transistor as a switch. And then we will look at all these details, not all in one class. It will take a few classes, look at all these details, and look at their application of these things in the context of both electronics and in the context. That is for my class 12 students. That is tomorrow. Okay, that is which is Sunday morning for Sunday morning IST for all of you. With that, I'm going to close for today, and then we will discuss that tomorrow.